Okay, welcome everyone. This is the third workshop of the AI workshop series, and we're going to talk about neural networks. So, neural networks are a type and one of the most powerful types of machine learning models. In fact, all of the very powerful ones that you see today, your ChatGPT and all of the other powerful large language models, they're all just very large versions of neural networks. So I thought that we would talk about the different components that make up a neural network. So things like weights and biases, activation functions, and certain other concepts that are really useful in learning how they actually work. And then, of course, at the end, we'll go through a notebook to see how we can actually build a simple neural network. So the first thing is to talk a little bit about the history of neural networks. So the idea is that, well, the human brain is something that is extremely powerful. And in fact, it contains billions of these things called neurons, and they are connected to each other, called synapses, and there's trillions of these connections. Each neuron is connected to roughly another 1,000 neurons. And so there was this idea that, well, what if you were able to take a biological neuron, which looks something like this, and have a computer replicate it? If you could build a computer which could have, roughly the same number of neurons and connections, then potentially you'd be able to create something that would be like the human brain, right? And something that could potentially give you like a human level of intelligence. So if we go into what this neuron actually is, you'll see that basically there's three main things here. You have this section here, which is at one end of the neuron, and you have these things called dendrites. And you could imagine that here is where you get your input. This is where it receives messages from the other cells, right? So from other neurons that pass information. That neuron would be this whole thing that you would be getting input from other neurons. Then you've got this main body here, right? And this is the axon. And essentially the main thing here is that there is an action potential. So when inputs are collected at this one side, it's passed through this axon, and there is a certain action potential that if the electrical signal exceeds a certain amount, then essentially these, at the end here, these terminal buttons, which you could imagine as the output, is basically turned on. And then when there is another neuron with more inputs, it will be able to pass a message and say that, there is some signal, that this neuron has detected some signal. If we were to break it up, what you have is an input. You have some way of computing this action potential here in the middle, and at the end you have an output, which goes into another input. So if we were trying to build this, the very simplest way of doing it is what we call a perceptron. And so this is the most basic human neural network. We take even the same structure of the neuron, the biological neuron, and we just make it into what we call a perceptron. So the perceptron will have a certain number of inputs. And here there's an example. It has 4 different inputs. And then each of those inputs will be connected to a weight, as you can see here, right? And this weight will determine how important is any of this one input on, say, the output, whatever we're trying to predict. If you take each input and you multiply it by the weight, and you sum it up against all of the inputs and the weights, you get this weighted sum. So as an example, if you had, an inputs of, let's say, 1, 1, 2, and 3, and your weights here were, say, 0, 1, 2, and 1, you would do 1 times 0, so the top one would give you 0. The second one would be 1 times 1, so it would be plus 1. The third would be 2 times 2, so it would be plus 4. And the last one would be 3 times 1, which would give you another plus 3. So that's as simple as what this weighted sum does. It just takes all the input and it multiplies it by some weight, which is like how important that input is. So if you sum this all up together, you'll get 8 as the weighted sum. Now here, there will be an activation function. And we'll look at these in a bit more detail, but essentially it's just if this value, the weighted sum, is larger than another value. So let's say we set it to 5. If it was greater than 5, then maybe we output true. And if it's less than 5, then we can output false. And very simply, we've now built this very basic neural network that can take a series of inputs assign some importance values to it, compute the weighted sum, and then check if it's greater than a certain value. And then it can decide whether it's true or false. The method that I showed of when you take certain inputs and you multiply them by the weights and you compute the sum and you go through the activation function, that's what we call forward propagation. So it's propagating through the network from one part to the next. And it's called forward because we're going from the left to the right. But we can make it much more complicated than that. We could combine different perceptrons together. So you can imagine now that if I have a perceptron, and I'll draw it as simply as 3 input neurons going to 1 output neuron, and you could imagine that I have all of these connections here, right? And each of these lines, say, instead of having the separate weights separated, we can just say that these themselves are the weights. So these lines will have a certain value. We could just add another neuron here, and we could join all of these up as well. So now you've got 6 different weights. So you've got 3 inputs and you've got 2 neurons here, and each one of the input is connected to the output, right? So the first one's connected to the top one and the bottom one, etc. And then we can do the same thing again. So we can have another neuron and we can just combine it like this. And we can keep doing this for as many of these, what we call hidden layers. So we could have, we could just do something like this and we could just keep making it larger and larger. So here, for example, we've got 2 hidden layers. You've got your input on the left here, and you've got your output at the end. And now what you have in the middle is your 2 hidden layers. And of course, we don't need to have just 2 neurons in each of these hidden layers. We could have much more than 2. You could have 10, 20, etc. It doesn't really matter how much you have. In terms of what it would look like if we were to, use some numbers. So if we take the normal perceptron, so the standard one, which just has 1 weighted sum and 1 activation function, what it looks like is when you have a graph, and let's say I had 2 points here, which are crosses, they belong to one class, and 2 circles, which belong to another class. A normal perceptron, all it's able to do is draw a single line. So I could draw a line here or a line here. But what I can't do is separate out the circles from the crosses, because it's not possible. This is what we call a non-linearly separable problem, because I can't just use one line to separate the crosses from the circles. But with a multi-layer perceptron, what I can do is I can have one of them, right, which is really good at cutting off this section. And I can have another one which is really good at cutting off this section. And then if you take these and you let's say, combine them together, what you can do is you can create this like non-linear boundary, which would go from here to here. So let's say everything in the shaded region could be one class, and everything in this shaded region could be another class. Part of the same class. And what's in the middle could be from a different class. And now you've created this like non-linear boundary. And that's the power of these multi-layer perceptrons. It's that you can look at these non-linear relationships on how your inputs may interact with each other. So there's a couple of components in the neural network. So let's look at activation functions. So before I made a very general oversimplification by saying that, if the 8 was greater than 5. But in reality, it's not really like that. What you have is from the weighted sum, so the weighted sum would be on this side here, you can put it through any of these different functions. And what you would do is, if you imagine x is the weighted sum, then you can look at the y value of any of these graphs, and it will tell you what the value should be after your activation function. So the very simple one that people would have used before in, let's say, a logistic regression is the sigmoid function. So it's this idea that after a certain value, say here, it will just be a 1. And if it's below a certain value, say here, then you will say it's a 0. The most common one that's used is this ReLU here. So the idea is that whatever the value of the weighted sum, we'll preserve it, right? So we'll always keep that value of the weighted sum. But if it's 0 or negative, then we say it's zero. And it kind of makes sense. If a value is negative, then we don't want it to matter in our computation. So we give it a value of zero. So it would give false. Otherwise, we can give it value of x and then give it to the next neuron, or it is the output of our neural network. We can also use neural networks not just for classification, so a true and a false, but you can use it to give you predictions for certain numbers. And we can still use these numbers for classification, but you can imagine that if I have a network here with 5 inputs, 4 neurons in the hidden layer, and I've combined all of them together, right? So every single input is connected to every single hidden layer, which will make 20 different connections in total. And then I combine all of the hidden layers with every output neuron, right? So that would be another 4 inputs times by the 3 outputs, so another 12. I essentially have here 32 different weights, right? 32 different lines here. We all have a different value depending on how important what came before it is on the value itself. And then, of course, what comes after it. There's another thing called biases. So sometimes we know, say, if you were to look at the prevalence of a certain disease, you know that maybe only 1% of the people have it. So what you want to do is you want to, let's say, give a bias to your network and say, you know what, the starting value of, let's say, this neuron will be something very, very small, right? So we could say, let's say 0.01. And the idea is we are telling our network that, be careful, this, whatever you're getting from your inputs, it, whilst, it may help you get the output, the starting probability to have that output is, let's say, 0.01. And you could have another one, right? Let's say you had a different kind of disease, or let's say one of these inputs was really, really important. Then, of course, the weight will be really high. So these biases are just ways in which that we can have a starting value for each of these neurons that they're able to use to use as a basis for then the different weights that we have to compute and multiplying them by the inputs to give us the output. Now the other thing here is the actual probabilities at the end. So you see here at the end we've got 3 different values: 0.1, 0.6, and 0.3. The idea is that, let's say, each of these refer to a class, right? So let's say this was a cat, this was a dog, and this was a turtle. What we can say is we can have each of these output neurons to represent a different class. So this one would tell us that the chance that it's a cat is 0.1, so 10%. And for a dog, it's 60%, and for a turtle, it's 30%. We can use this because rather than having, a specific model to check, is it a cat, and another model to check, is it a dog, and another one for, is it a turtle, we can build a more complex neural network that's able to have all of those outputs, all of the different classes in the output, and we can just look at the highest one. Whichever one has the highest probability, we probably assume that this network, depending on all of these inputs and these weights, says that that input is a dog. If you imagine here, a little more practical example, we can look at some of the inputs as, let's say, this is a neural network that's trying to predict the destination and the class that a passenger will be traveling at. You can see the model is taking in the age, their job, where they're coming from, the month of the year, and the day of the week. And by combining all of these weights, they have 2 different networks, 2 different classifications from the same network. So if you take all of these inputs, you're able to get whether they'll be going to Paris or London. And of course, this could be many more cities. It doesn't just have to be 2. And then here, it's also using the same inputs, but with different sets of weights. So you can see the different weights. Everything's connected if you look in the gray. But the ones that are important are the ones that have been colored in, right? So all the red ones are important to work out the destination, and all the green ones are important to work out the class. But we can do all of this in one network, one larger network. And this model ideally would be able to learn, where you're traveling and what the class is, depending on these input features. But the problem is that if we try to investigate what's going on, right, in this network, right? So of course we can go and we can look at the value of, let's say, what this weight is, and we can also take a look at what this bias is. But the problem is that it's not very clear what this whole network is doing in general. And that's the problem that we call that neural networks are black box models. They're not very interpretable. They can give us really high accuracy. They're really good at computing, our outputs for whatever problem we want to have because they're able to look at that non-linear relationship. Of course, they can look at the linear relationships, right? So it would make sense that if a person's job is something that gives them more money after a certain point, let's say if they're making a few 100,000, it's likely they may always go for first class whenever they go on a flight. And if it's under that amount, then you may say second class. That's just an example. But with the non-linear relationship, it's difficult to understand exactly what a model's actually doing. For why does it say that, based on all of these things, a person's likely to go to a certain destination? Now, that's all about how these models are able to, these neural network models are able to, we can use them to compute an output. The difficult thing is how they actually learn, how they learn to do the task that they've been given. And what it's called, this task, it's called backward propagation. So forward propagation was when you start at the beginning, you look at the inputs, you multiply them by the weights, take the sum, check if it's greater than or less than a certain value, and then you give an output. Backward propagation starts from the end. So what we do is, let's say we had a certain number of inputs, and it told us that the output was true. But let's say in our data, we actually know that it was false. So what we do is we can tell our function, our activation function, that look, your boundary was wrong, that this one should have actually been false, not true. And so the activation function can then tell the weighted sum that these the output that you gave as true is wrong, it's actually false. And so what the weighted sum can do is it can look at each of the different weights, right? And it can look at the value of the input that came to it. And what it can try to do, at least, is that if it realizes that any of these inputs and weights contributed to, giving it true, we can reduce the weight because we can't change the input; those are fixed, but we can change the weights, right? So if let's say the weight before was 3, maybe now because we're looking at trying to get it to predict false, we want to make it a smaller number so that it predicts it as false. So we change the weight from 3 to, let's say, 2. We don't want to make a huge difference straight away. We can take incremental steps and we can keep doing this again and again. So what you would do is then you would check every single weight against the input, and then depending on how large the input is, and of course you can imagine if this was a much larger network, each of these inputs would just be another neuron in our multi-layer perceptron. We can just change all of the different weights, and we can increase them and decrease them, whatever we need to do, right? So let's say one of these inputs was one of the weights that was corresponding to an input was very negative. Maybe we say, make it more negative. If it's -2, make it -3 or -4. Now, the actual maths behind it is a little bit more complicated, and it's to do with partial derivatives. But there's an excellent series by 3 Blue 1 Brown. You can find it on YouTube, and it goes through in a very nice level of detail about neural networks, gradient descent. So that's the first kind of basis, the first kind of foundations on how this propagation stuff works. I really recommend it for anyone who wants to learn more about the maths involved. But that gradient descent, so we can look at it. So the idea is that every model, right, every neural network, if we have, it doesn't matter what the weights are, what the biases are, if we evaluate it on a set of inputs and outputs, we'll get a kind of score, right, for how good our model is. So in this case, the model has begun on the black circle at the top, near where it's red. And you can imagine that the more red it is, the worse the model is, and the more blue it is, the better. And so when we are doing that back propagation, when we're trying to fine tune our weights, we're trying to change them to go up and down to try and give us, the maximum score, so that everything that was true in our data set, our model predicts as true, and same with what's false, is that we can look at, how roughly wrong it was. So let's say here, we have a really high error rate, and that's why we're so high up. You can imagine that what the model does is by changing the weights, it slowly starts to go from the top and it gets all the way down. And eventually what it will do is it will try to find, the best, most optimal way to try and change its weights and its biases to end up at the very bottom where ideally we have the least error. So if you imagine that at the very top here, and at the very bottom here, we've got a high error rate, and then on the very bottom, we've got a low error rate. And what we want to do is, of course, make our model as accurate as possible. We want to bring it all the way down to have as little error rate as possible. And if we look a little bit more about the maths behind it, if you imagine that here the cost is, how good that model is. The model starts somewhere on this curve, right? And we can roughly know that where the model is now, with the current weights that it has, we know that in what way would changing the weights give us the fastest increase, so that would be the first arrow underneath it, to achieve that minimum cost. And that thing is what we call the gradient, right? So we can look at the features we can look at the weights of our neural network, and we can look at in what way we can change them. So every single one of them, we can make a decision to make it higher or lower, and by how much. And we can see with the red arrow how what kind of performance increase, so how much better the model can be if we were to make those changes. And we can measure that with this gradient. And what we want to do is we want to keep following this. We want to keep following this all the way until we get to that minimum cost. At this point, basically the gradient is zero, meaning we can't go any left or any right. You can imagine it's a ball rolling down a hill. We've reached the bottom, and that's it. And one of the problems with that is that because we're just rolling down a hill, it's possible that you end up in these things called local minimums. So if you imagine that there's, an infinite number of potential weights and biases that you can have for your model, when we start, we're just randomly selecting them. And of course, we would want to have this global minimum, right? The absolute best model, the lowest point from any of these other, smaller local minimums. But when we start randomly, the model will start in one of these areas. And we have no control because we don't know exactly how this model, we don't know about exactly what the best one is. Otherwise, we would have placed it there straight away. It's an iterative process to try and find the best next weights that help us reduce the error of the model. And so you can get stuck in these local minimums where at that point, you can't go any further down because all the model will know at that point is what's on the left of it and what's on the right of it. And if it reaches one of these points, it will never be able to get to that global minimum. So whenever we build neural networks, it's always a good idea that we try different starting positions. And maybe we'll end up on something like here. And if we end up here, it will help us get to that global minimum. And in practice, a lot of these minimums are very, very similar. And it's rare that there is a global minimum that's significantly different from the others. But we can always try multiple experiments to see roughly which model can get us the best result. Now, if we look at these arrows that take this model down from one position to the next, right? So that arrow represents changing those weights and biases. We can talk about this as a learning rate, right? So if you imagine that we were only going to make very small steps. So before I show the example of changing the weight from 3 to 2, because we want to make it smaller. Well, what if we only change it from 3 to 2.99? So we only changed it by a very small amount. What will happen then is that we'll need lots of these changes, right? So you can see the amount of arrows, it's a lot before getting to that minimum point. I actually moved to the other one first, but there's also a problem if it can be too high, right? So if the error rate, so let's say I went from 3 all the way to -3, maybe that causes such a big difference in what my model does that it just starts jumping all over the place. And it's not even able to find the smallest point. So what we need to do is find this exact, this like optimal way of changing those weights, because we don't want to change them by too much or too little every single time. And so what you could imagine, right, very simply, is if we start by changing the weights by, let's say, 1, and then every, 10 times we change the weights, we change this. So, okay, instead of changing it by 1, let's change it by 0.5. And then let's say after, I don't know, 100, now we only change it by, let's say, 0.01. So it's like at the very beginning, we can change our model by a lot because we don't know how good our model is, and usually they're not very good. In the middle, we can change by a little bit less than that because we're starting to get closer to the final solution. And at the very end, what we assume will be close to our best model, we can use a very small learning rate so that we can exactly get to where the best model is. And we don't overshoot it and we don't undershoot it. And it takes too long. Now, when we take those values, right? So if you take those observed values from your data set, which tells you, these are true and these are false, and you look at your predictions, which tell you, right, given the inputs, true or false. We want a way, right, to actually like mathematically know when our model is performing well and when it's performing bad. And a simple way is to use what we call loss functions. Right, so all neural networks use these loss functions, but different kinds. So here's an example where the model is the dotted line, which I'm now coloring in red, and this is that best fit. So if you look at all these data points, which are blue, the line of best fit is the one that's red. It goes roughly through the middle of all the points, and yes, there's some error, right? So you can see this residual error where the blue is where where the actual value is, but our model, because it's just a straight line, it will just take the x value and it will just give you the y value of the line, right? On the left side, we actually have its actual y value. So you see here that there is an error, right? And we want to be able to reduce that error. Now, in this example, we've already got the best line, but the way that we do that is we use this metric called the mean standard error. Essentially, you take the sum of every single data point, every single one, and you compare how far away it was. So that's your actual values that you got from your data set with the model's predictions, and you can just sum all of them up. So you can sum up all of these distances, like just a straight line between them, and you can divide by the total number, right? So divide by n, and that will give you roughly the average of how much error you have per prediction. And you can do very, very similar things for other tasks. It doesn't just have to be predicting a number. It could be for classification, other problems that you might want to solve. But what you need is a loss function. And standard libraries that we use now to do machine learning, they always use default, loss functions, learning rates, etc., which are generally sensible. And we only really start to modify them and change them when we see that our model is really not performing well, or when we really need to get the absolute best model. So there is a very common data set which is used in machine learning, and it's called the iris data set. The idea is that there are these three different types of iris flowers, right? So you've got this setosa, this versicolor, and this virginica, and each of them have these petals and sepals. So you see that the petals are the ones which are on the outside, and you see the petals are the ones on the inside. And this data set will have the class, so it will tell you which of the types, the species of iris flower it is. It will have the petal length and width, right? So how long the petal is and how wide it is, and also the sepal length and width. So by using these four features, the idea is that this data set could be used to help teach how we can take certain features and then predict a specific class. So we're going to go through this together. So I have a repository here, and I will copy the link into the chat. And there is a Google Colab, and that's what we can use to run the machine learning, to run the notebook. So I'll just copy it into chat now. And you don't have to do this at the same time. You can do this afterwards. I will just go through this and share my screen. So inside the repository, the folder for neural networks, there is a notebook.ipynb file. And if you download it, and I'm also just going to download these other files because they are images that we can use within this notebook. We can then go to the Google Colab and we can upload the notebook. And we'll let this run. Then click connect. And in the meantime, we can upload those files. So there's those images that I wanted. Right, so this is an IDE. So it's a development environment that we can use to write code. It's offered by Google. It's completely free. So you connect to a server. You can put in your notebooks here, your Python code, and you can work through this notebook. But of course, you can work on your own projects as well. What I've done is I've listed some information, but here we're just going to go through the actual code itself. Right. So this is going to be roughly how do we go from taking a data set, maybe different data sets, and how can we, run some neural networks? So the first thing that's very important is that there's two main libraries for working with machine learning that let us build, more serious neural networks. And they are TensorFlow and PyTorch. So TensorFlow is one that's offered by Google, and PyTorch is one that's offered by Facebook or Meta. And here we just got some different libraries so that they'll have different functions that we can use to help us with dealing with numbers and tables and plotting. So I can start slowly running each of these code blocks, and you'll see I get the output underneath. I don't think that will matter. So here, what I'm doing is I'm loading the iris dataset, right? So it's using a specific package to load this, but of course, if you had this yourself, you could just change this with where your dataset is stored. And it tells you here that it has 150 flowers with all of these different columns, so sepal length, sepal width, petal length, petal width, and its species. And it can be either one of three different types. And we can print the head, right? So we can look at the top 5 columns and you can see roughly what it looks like. We've got different numbers, probably in centimeters, for how, wide and how long each of the sepals and the petals are, and the species. And you can see 150 different flowers are in this data set, and 5 is for the different features, right? So the length, the width, again, the length and the width, and then the species. And it tells us that out of the 150, we have an exact even split. So each species has 50 different examples in this data set. Now, one thing that we're going to start by doing is, whilst we can predict, we can have a specific column and we can predict Setosa, Virginica, and versicolor, what we'll do instead is we'll use that similar idea that I showed with the cat, dog, and turtle. So rather than having a single output that we have to choose which one to represent, we'll have an output for each of them. So we'll have an output for Setosa, one for versicolor, and one for Virginica for all the different species. And what we'll tell our dataset now is that, if it's a Setosa, make it true and make the other 2 false. So then our neural network we can use to predict all 3 at the same time, and we can just take the highest probability. And that'll be really simple. And that's all this part is doing here. Now, once you've got your data set, immediately the next thing you want to do, obviously, usually is to look into, the data itself, right? So we want to look for missing values and we want to look for the different features and whatnot. And you can go back onto the workshop 2 for building the machine learning pipeline to see more about that. But in this case, we're just going to skip doing any fancy stuff and we'll go straight into building the model. So what we will do is we will split the data set, right? We want to have a guaranteed holdout test set, because what we don't want, is to train our model on all of the data and it overfits, meaning that it learns basically by memory all of the 150 flowers and it can't predict anything new. So we'll pretend like this 30 contain the same and similar values of the data for the flowers, but we're gonna pretend like we're not seeing it. So we're gonna focus just on this training set of 120 different flowers. And you'll see that it's 4 now because we've removed the species. Because of course, if you gave the actual species as an input, your model would just focus on that and get it right every time. From here now, we can build a neural network. So here what we have is we're using the Keras, so this is part of that TensorFlow package. And what we can do is we can build a neural network. So here what we have is a single layer. We're going to use the ReLU activation function, right? Which means that if the weighted sum is 0 or less, we'll just pass through 0 to the next neuron. And if it's greater than 0, then we will give the same value. And we know already that it will take 4 inputs, right? 4 inputs here, and we will output 8 neurons. 8 neurons. And then we have our hidden layer, right? So this is, this will be the second hidden layer because this is also a hidden layer. And this will just take the same inputs, 8 inputs, and we'll have 8 more outputs. And at the very end, we will have the 3 outputs for the different species. And this activation for softmax, basically, it just helps us deal with when you've got more than 2 different classes. It can give us just the probabilities for each one summed to 1. Because otherwise, sometimes the probability will be really, really small. But if you compare them to each other, one is actually much more likely than the other. So as an example, if the probabilities were 0.1, 0.1, and 0.1, it's not 10% chance of being each, it's actually 33. It's just divided by the sum of 0.3. Now here, this model.compile, we're just using some standard stuff that the packages have. Main thing to focus on is that this model will try to get the highest accuracy possible. And when we run this piece of code, it will show us that we have the different layers. So it shows us the first layer has, of course, we have our input first, but then our hidden layer starts with 8 neurons in the first hidden layer, 8 neurons in the second hidden layer, and the 3 output neurons. And it gives us a total number of parameters too. And this kind of makes sense. So we have 4 inputs that are fed into 8 outputs, right? So 8 neurons in this hidden layer. And if you multiply that together, you'll get 32. If you add on each of the bias for each of the neurons here, you'll get 40. And the same thing here. So if you take the 8 neurons from the previous hidden layer multiplied by these 8 neurons, you'll get 64. And if you add on 8 again for all the biases, you'll get 72, etc. And the interesting thing is, like, 139 parameters is a really, really small amount. That's just 139 different numbers. So that's that's weights and biases that we're trying to fine tune, right? So we're trying to do that gradient descent, that backward propagation to figure out what are the best values for all of these 139 different numbers. And it tells us how much memory that model takes up. So 556 bytes is very, very small. It's a very, very small model. Once we've built the model, the next step is to now train it. So here we will give our training data set, we will give the labels, so we will tell it whether or not, which species it was. The epochs here will refer to how many times we will do that back propagation. So if we take all of our inputs, we put it all the way through once, and then we check what is the, we can get the accuracy and we can predict with it. We could consider that as one epoch. 50 epochs means that we're just going to do that process 50 different times. So we will change our weights again and again, at least 50 times. The batch size will tell us, after how many times should we then change our weights, right? Because you could change after every single one, but then you're doing a lot of extra computation you might not need. So why don't we just take, let's say, 8 at a time, take the average amount that we need to change our weights and biases, right? So we have a batch size of 8, and then we will update the weights. Now here it says there's a validation split. So the idea is that, we have our test set, but that's for later. What we want to do first is we want to test how good our model is. And what we can do is we can do something really smart by having that validation set. And again, if you go back to the workshop 2, which is uploaded on YouTube, you can see exactly what does this mean. But as a very brief summary, it tells us how we can have a holdout, like a temporary test set that we can use to tell our model how much to change our weights and our biases so that it's not overfitting our data. And if we run this model, and it sometimes will take time, we're going to let the model train, and then we're going to evaluate it onto the test set that we created initially with 20 different samples. And it says here that the test accuracy is 1. And if we're to draw it, you'll see here that the training accuracy, you see after about 20 epochs, it really starts to increase, right? So after a while, maybe it's trying to change those weights and it's not able to, figure out exactly, the differences between why, the different species are the different species based on the input data, but eventually it gets really good. But we see something here with the validation accuracy, and this is something that's really not good. What we don't like to see is when the model goes up and down a lot. The reason for that is chances are we might be overfitting now. When your validation accuracy and your training accuracy start to overlay each other. So here what I did is I ran it again. And the reason why it's different is because I'm not, the neural network starts with a set of random weights and biases. So here, it's just another example. So I ran it again with another random set at the very beginning, right? So you see it's not very good at the beginning, right? 0.3 means that on average, the model was just randomly guessing. But at the end, you can see like all of these jumps means that we're probably training either our model for too long or that we have to configure something inside the model so that it doesn't do this potential overfitting. Now, this here is just a very, very simple data set and an example of what we are able to do in terms of building a neural network. So now what I want to do is to use a different kind of data set, and this is a data set with images. So what we have here is, again, importing all the different packages that we'll use, and each of them will have specific things that are useful. We're going to use this data set called the MNEST data set. And what it has is 60,000 training images and 10,000 testing images, each of a handwritten digit from 0 to 9. So it's single digits from 0 to 9. And this this data set contains 70,000 different images, much more than the 150 we already had. And we get some extra information. So each image is 28 by 28 pixels in grayscale. So here it was loading up the data set. And we can look at some of the examples. So here, just 6 different examples of those images. You can see here the label, so what is stored in the data set, and what is the image itself. These are pretty normal, makes sense, right? You've got 5, 0, 4, 1, 9, and 2. And some of these ones in the data set are much more complicated and difficult. So you'll have numbers which look very similar like other numbers, which could probably fool some humans if we were to try and guess it. And the goal for that is just to try and give the neural network a good amount of representative data, because people's handwritings are different. Some are clearer and some are more difficult than others to read. So from here, what we do is we take the 60,000 images, and rather than having an image of 20 by 28, we just stack it up together against each other. So again, in the previous workshop, what I showed is we can't just give an entire image to a network, to any model. What we usually do is that we take the first row, and that starts at the very top, and then we take the second row and we just put it underneath that first row. So instead of having 28 rows and columns, you would have like 784 inputs. So you've stacked all of the different columns against each other. But we know a neural network can deal with that, because even if they're farther away from each other, because every single input is connected with weights, the model can learn which of these pixels are close to each other. Here we're just normalizing it from 0 to 1, because of course the grayscale will be on these RGB, not RGB, but the intensity of the pixel from 0, which is black, to 255, which is white. So we just make it from 0 to 1 to make it very, very obvious and clear to us, when there is white, so when there is a number in the image, and when it's black, when it's just a background. Here, what we're doing is that we don't want to, again, have one single output that either gives us 1, 2, 3, up to 9, and 0. What we'd rather have is that every label, for example, a 7, would have 10 different output neurons, but only the one which corresponds to it correctly will be turned to 1. So if you imagine it was 0, 1, 2, 3, 4, 5, 6, the 7th one will be turned to 1, and all of the others will be 0. And by this method, we can have one single network that can predict all 10 different numbers. Here, our network is a little bit different. We're only using one hidden layer, right? So we take the 784 inputs, and we have 128 neurons in the hidden layer, and we have our 10 outputs. And when we look at this, you can see 100,000 parameters, right? So you've got 784 inputs multiplied by the 128 here, plus the 128 again, right? So, and it takes up, over almost 100,000, not 100,000, sorry, 1,000 times more memory, this model than the previous one. And it makes sense because, of course, the data set is, the number of inputs and the neurons in the hidden layer are much larger than we had before. And again, we can train it. And here we're only going up to 10 because we just want to test how it looks for now. You can see we're changing our batch size to much higher amount. And that's because we don't want our model to overfit too quickly. And we also want it to train quite fast. So the higher the batch size, technically, the faster the model will train. But it might not perform as well as if you did pick, say, 64 or even just 10 or anything smaller than that. And then we have 10% for our validation set. And when we do this, we see lots of these metrics. So we see that in the first epoch, so the first time it was running this model, it had an accuracy of almost like 82%, which isn't bad. So just by looking at the images, so all 60,000 after dividing it by the test set, gave us an 82% accuracy, which is not bad. Meaning every 10 images, it got 8 correct. But you can see that once it trained properly, right, so it completed all the different batches and we ran it for a second epoch, so now it's going to look at the same images again. So at this point here, each of these 422 is a single batch. But when we get to here, we're looking at the same images from the previous batch again. So now at this point, we're looking at images more than once. And so again, when we do it, you see it jumps up, right? It was 95% accuracy, which is much, much higher. I mean, we talked about the loss, right? So the loss functions, we don't exactly know what these, what these actual numbers mean, but all we want is we want to make them as the loss as little as possible, right? The loss function referred to the way that we compute the error from our predictions and our actual observed values in the data set. And after 10 epochs, right, so after just this amount of training, it gets to 99% accuracy, which is actually really good. And if we plot this, you can see here, you can see that the model, even right at the beginning, obviously, yes, it was about, 82%. And when we tested it on the validation set, it was almost 95 and a bit percent. And you can see just more training and it got better and better. And yes, we can go back and we can change this epoch, so you can make it, 50. We'll do 25 because it will take time to run. And what this will do is it will take from the model with which had already been trained up to 10 epochs, and it's going to add another 25. So what we're going to see here now is a model that's ran for 35 epochs because we're just going to train the model again, exact same. While it runs, we'll go through the next couple blocks because this may take some time to run. When we put it against our test set, we see that the accuracy was about 97.5. So it's a little bit worse than it was on the validation set, which makes sense, of course, because the validation set was not, the test set, none of those images were included in the main training or validation set, right? So it was unseen data. Maybe this is broken, so we'll just leave this for now. You're always free to go back and check it, try it with different numbers and see what you can get. So here, now, what we're doing is we're going to predict the actual classes on the test set because I just want to be able to show you what this model is doing. So this is a confusion matrix. So you had to take all the predictions on the bottom and all the actual values on the left, and it doesn't matter which way, people have different methods. And obviously it doesn't need to be as complicated as this for your problems. If you're just doing a true and false, you would just have 4 squares. You'd have a true positive, a false negative, and a true negative. Here we're looking at every single prediction against the real value. So it's a 10 by 10 grid. So in the top left, you see that 969 times that the value was actually a 0. We predicted it was a 0. But you see here, if you go down, we didn't always if we go across the other way, we didn't always predict it to be, the value that it was. Sometimes you predicted it as a 2, a 3, a 5, 6, etc. And some of these numbers are larger, right? So it confused here clearly between a 3 and a 5 a few times, right? Again here. And we can use this to look into, where was the model better and where was it worse? So as an example, it was really good in general at picking out the ones, right? It's almost 200 samples additional numbers that it was able to get correct. And then for each individual number, we can also look at its overall performance. So we can look at the values for, how often did we get it correct? I know these metrics have different meanings, but just in general, because we have a balanced data set, the important thing is that, well, the accuracy is about 97%, which is good, but it does mean that out of 100 images, you're getting 3 wrong. So if you imagine you wanted to put this into, let's say, a postal service, right, and you wanted to build an AI that could automatically look at the different numbers for, let's say, the address. Well, if it's going to get 3 out of 100 wrong every time, that's a lot. That's a lot of potentially, thousands or millions of packages that will be sent to the wrong address. And that's why we're going to look at that in the next section with another kind of model. So here we can look at the some random images, and we can look at the true value and its predictions, and here it's all correct. Now, what I had here was I was like, well, the MNIST data set is nice and all, but let's test it on some actual, my own images, right? So that's what I put in here, right? These tests 2, 3, 4, and 7 are these images. So I drew this red 2. And of course, the first step, because we want our data to look like the MNIST data set. And so the important thing is the MNIST data set is 28 by 28 pixels. The background is black and the number is white. So first, let's make it grayscale. Let's make it 28 by 28 pixels. So we'll downscale it all the way so that it matches the same dimensions. And we'll make it so that, background is black and the text is white. And again, we run the model on it, and you see that it actually predicted it correctly. It predicted it as a 2. And here, when we look at the probabilities, you can see here, it predicted with about an 80% confidence, probability that this number was a 2, in fact. Now, what I had here was a way that I could run this model on different images. So here I drew a 3, but I wanted to kind of trick it because I thought maybe I could get it to predict a 2, and it did. Here, it wasn't very confident, right? In fact, it guessed only with a 25% confidence that it was a 2. The correct one, obviously this is a 3, still 16%. In fact, it thought it had an equal chance of being a 3 and a 4. An even higher probability of being a 7. So clearly it's like this model here could be better, because there's, this is very common that you'll have a number like this in the real world, somebody to draw something like this. So you'd want something that's better. So now, this is the last kind of model, which I didn't put in the slides, but I thought I would just talk about it very briefly. The neural networks that we've had so far just take every single column of the image and they stack it, right? So this first column stays there. The second column, we'll move it underneath the first one. And so by the end of it, when you go to the last column, you've separated this top right pixel from this top left pixel, right? One is at the very beginning, at the very top of your inputs, and one's pretty much at the very bottom. And the reason why that's a problem is because if you imagine here in the middle, right? So if you imagine these pixels here in the middle, where you've got these 4, these are all right next to each other in the image. But when we're splitting it up, we're separating them by so much. And whilst it's true that a neural network can, because it has all of those different weights, it may, potentially be able to find the that these are somewhat close to each other. Unless the model is really, really large, it won't be able to. And we don't want to have a very, very large model. We want to have, an efficient model that could be used in practice. So what we can do instead is we can build a model that uses the actual spatial understanding. So what we're going to do is, rather than looking at, each individual column and then stacking them on top of each other, instead what we'll do is that we'll look at blocks of them. So let's say we call them patches. So we'll look at the top left, and then we'll move a little bit. So we'll look a little bit more to the right, and then again a little bit more. And the idea is that now, rather than just looking at individual pixel values, we can start to look at the different patches. So the potential different, the spatial features of this image. So we can start to look at the different edges. So what we have here is what we call a convolutional neural network. And so the way that it works is, here we just take a very small grid, right, of 3 by 3 pixels, and rather than having, a hidden layer at the very beginning, which has, 128 different weights, we have 32 of these different kernels. And so because it's 3 by 3, you can just very simply imagine one of these kernels of these 32 is really good at looking at a straight vertical line. Another one is really good at looking at a diagonal line, going from the bottom left to the top right, etc. So each of these filters of all of these different kernels, we're really good at picking out something very, very specific. But of course, 3 by 3 is a very small grid. So we're looking at the very small different features. And if we do that, what we can do is we can, instead of looking at the image, by 28 by 28 by itself, we can start to look at the different, potential features that we see in that image. So before I mentioned that, a network could look at the image of a dog and it could try and pick out its mouth, its nose, its face, etc. And this is how we can do it. I won't go into the details exactly of the CNN. Again, there is a very, very useful video, but again by 3 Blue 1 Brown, which talks about what is a convolution. And it's a great video that explains all of these different steps. But essentially here, we have a much more complicated model. It's 225,000 parameters, which isn't that much larger than the one that we had here. This one was, if we got back to it, 100,000 parameters, which are taking up 400 kilobytes. And if we go back to here, we will see that this model has 225,000 parameters, about 900 kilobytes. So it's maybe double the size. And when we train this, and we're not going to change the setup too much, right? We still want to use a validation set of 10%, we still want to have 10 epochs, and we still want to use the batch size of 128. Because let's say we want to compare the model. You'll see that this model is starting to get much higher than the initial model that we had with a simple neural network. And obviously, the better way to look at this would be that if we trained it for much more than just 10 epochs, but you can see here the difference, right? So if you remember the old graph, right, where we started off at the bottom with the validation and we went to the top, and there were also different like bumps. It went up and down. You see here that we have a very consistent accuracy, which suggests that this model is actually able to learn the different features, right? So the different kinds of lines and edges that are in the image that, when you combine them all together, could help you understand if something was which digit it was. And here, yes, you see 99%. So before it was about 97%. So here we're still getting 1 in every 100 wrong. And the way that we would go about this is we train it for much more epochs. Maybe we try test different things in our setup. So maybe we change the different parameters and the different number of layers and all of the different configuration in this model. But we can just use the same libraries and very simply, and I will draw your attention to this, that this is the entire neural network model, right? Something that maybe we glance over is that it's actually really, really easy to build these models. And what we can do, for example, is we can always use the generative AI features, right, in these IDEs that could help us, right? So if I wanted to say, this model is good, but I want to make it better, add more complexity, I can just write it here. And it will, give me suggestions to how I can make that model better. And yes, it's already came it straight away. It's done it in a little bit of a different way, but already it's giving me a model straight away. And this one, you can see here, has only 100,000 parameters. So what I assume is going on here is that this, this AI that was used to generate this bit of code is guessing that this kind of model, we expect to be better than the one here, maybe because of the different kinds of, the different layers that we have here in this network, maybe this one is better. And of course, you can use that to your advantage to figure out exactly, what does each of these mean, and you can ask it, what would happen if I was to add, say, another of these different layers or the different number of neurons in these layers, etc. We won't focus on this. What we can do is we can look at the very end where we have our confusion matrix again, and you can see we don't have those like those errors greater than 10 in these individual cells anymore. So if you remember, there was like a 14 or a 15 somewhere here where we were predicting a 3 is a 5 and now it's 4. And you can see across the board, this model is just better than the other one. And even though it is getting 99% accuracy, remember, if we were to put this in the real world, in a post office, let's say, to detect the digits, it would still get, the error rate is still far too high. And here we're just looking at some examples. And what I decided is that, I can look at the same image, right? The one that the other neural network predicted was a 2, and it was only 25% confident. And this one says it's 99% that it's a 3. So one thing also that you could consider is that, these different models, they might have, similar metrics. So they may have, very similar values for how well they perform, right? So all of these 99s means 99%, precision, or whatever these mean, 99% accuracy. But we can also see that there's other things that we could look at to do with, well, how confident is it, right? So this model is clearly much more confident with this. And if I say was to, so 4 and 7, I test now the model on, I realize this won't work now that I'm training the model here. So let me stop training it and let me see if this will work. See, because I ended the model earlier, it won't do it as well. So if I use your initial model, it would have showed me. But from what I had tested, is that it was able to get the 2 and the 3 and the 7 correct, but it wasn't able to get the 4. As far as I remember, it was still 1. That's just a brief overview of these CNNs. So these are a more complicated version of neural networks. And there are many more different kinds of neural network models, right? So the most common one that we use in these large language models, they're called transformers. So they're able to take huge amounts of data and are really good at being able to find ways of predicting, let's say, the next text, the next, let's say, word or character or sentence. I see there's a couple of questions here. So are the nodes in the hidden layer weighted sums, or are they perceptrons themselves? So in that example, they would have been weighted sums. So not every neuron that I drew was a perceptron. You can imagine that the perceptron is as simple as you have a set of inputs to one output. The multi-layer perceptron says that, well, why just have one output connected to all the different inputs with the same number of weights? Why not just have many more neurons? So you can have, let's say, 2 output neurons, or you can have a hidden layer. So you can take all of your inputs and give them to a certain number of neurons in your hidden layer, and then again put it through your output. So you can just continue to build that model to be much more complex and much more potentially powerful. We don't usually combine a perceptron with another perceptron per se. Maybe if you look at the definition, maybe that the perceptron is just taking an input and giving an output. So you are, but the better way to look at it is that it's just you're changing the number of neurons you have in your network, and I think that's an easy way to understand it. And I hope that answers your question. And for the second question, which package do you recommend, PyTorch or TensorFlow? So I think for simple problems, I would use TensorFlow. It's very easy to use for beginners, and it has a lot of support for it, of course. PyTorch, whilst it does have lots of support for it too, it's used much more for when you really understand each of those individual components of building your machine learning model. So, for example, with the neural network, if you don't give it, the certain things that I gave it, like the optimizer, which said Adam and the other things, and all I did was give it the metric of accuracy, it would still be able to perform it really well because it uses these default values, which are really good. Whereas with PyTorch, the reason why, well, I and other researchers use it is because it's really, it's really powerful at being able to change it, each of those individual components, and you can have a lot more flexibility in the actual training process. So straight out of the box, I can change it to do whatever I want to do instead of using, whatever the Google has offered me to say that, this is a good one, just use it. It gives you much more control, especially when doing research, to try and be really finicky in the details to try and build the best models. So I'd recommend TensorFlow at the beginning, and only when a person has gone through the maths and really understands what these neural networks do, then you could go into PyTorch. But both of them are just ways of building these models, and they're both very, very good. And most of the problems that aren't using thousands and maybe tens of thousands or hundred thousands of images and examples with very complex problems, TensorFlow will be just fine. And of course, you can use TensorFlow for the more complicated problems, but most people will use PyTorch. Are there any other questions about any of the other components within the neural network, or maybe in the notebook? And if you don't have any questions, then of course you can just email me, and I'll respond as quick as I can. I think there was one or two slides left, actually, I'm remembering now. So in the PowerPoint, I had listed just a couple of these potential things to consider. The whole purpose of let me just skip to here. The whole purpose of building these artificial neural networks is that we could simulate the brain. And the problem is that, well, the human brain is really, really efficient. So it uses only 23 watts of power, enough to power a light bulb. To run a neural network, you need to have at least a computer, and it needs a lot more power than just what's enough to light a light bulb. And of course, for us, our power source is renewable energy from food, right? But these machines that are going to do very powerful, very, very long and extensive computation to try and build these neural networks, train all of those weights and biases. They use up so much power, and it takes such a long time to be able to do that. And you see here that the most powerful computer, supercomputer, I believe, performs 1.7 exaflops. So it says here a billion mathematical operations per second, right? And we can perform our own brain roughly about 1 exaflop. And something like that uses 246 million watts, right? Which means that our brains are billions of times more efficient than these supercomputers, even if they're very, very good at performing very specific tasks. To do everything all together, when you look at the power that the brain uses for those neurons, and obviously it's a very oversimplification, we are much, much more efficient than these other, supercomputers when we give them all of these neural networks and whatever they may do with them. And so I think that's the last thing that I was putting on, is this thought process, this idea that, a lot of people talk about AI taking jobs and whatnot. And one thing to note is for certain that all the neural networks can do is take some inputs, and by neural networks, I also mean all of the big, large language models and these big AI models. All they can do is just give you predictions based on the data that you give it. And it's very difficult for it to do actual critical thinking. They can simulate it by trying to guess what a human would do, right? So given some, previous text, roughly what could come next. And yes, they're really good at having lots of information, and you can search things on that. And that's just like what you can do in Google when you go on a search engine and you type in something to look at what results you'll get. The difference is that we have, this aspect of creativity and way of thinking that these other, these computers, these models do not have. I thought I would leave it on that. There is a feedback form. I will copy the link for that if you wouldn't mind filling it in for this session. There is only one more technical, well, it's kind of technical lecture next week, and that's just on the ethics. So it's, that will be much more interactive. I think these two, because it's very technical, I thought I would treat them more as lectures. And then afterwards there will be a mini hackathon. So it will be in 2 weeks' time, looking at how we can go from finding data to solve a problem that you want to solve, and then how we could go about the whole machine learning process. So going right from the beginning to having a model at the very end, giving it new inputs and seeing how well it performs. Thank you all for joining. I will see you all next week.